Hi everybody, thanks for braving the rain and actually making it for the talk. So we'll actually get started without further ado because it's already a few minutes late. We have a pretty, I think, cozy audience here today. So let's get some, like maybe show of hands in terms of how many folks, maybe from like a product development background. Okay. How many folks from like a service background or service industry background? Not too many. Okay. How many of you are developers? Okay. And any product managers in the house? Product folks? One product. Okay. And how many folks have done like data for over 2 years? Data experience for more than 2 years? Okay. Okay. Few. Over 5 years of data? Over 10 years of data? What's that? Any kind of data. Cool. Awesome. Did you have any other questions, Pramod? Pramod made the suggestion. So if there are other questions that you might want to have, good show of hands. Okay. All right. So let's get started without further ado. My name is Subramanian. I'm an eng manager at Uber. I'll cover a little bit more about myself later, but today the talk will be largely about how we do data at Uber. We'll cover, this is actually 3 separate talks. We'll talk about data at Uber, how data moves and what are data challenges. We will not go deep into the challenges because that itself is like an hour's talk. We look at our data analytics infrastructure at a very high level, and we'll mostly spend time on kind of our machine learning use cases or how data science and machine learning is done at Uber. We look at some use cases, we look at some platforms that we have built at Uber for the purpose of machine learning and data science. And we'll also look at some intersection of the two. That's an interesting topic in the industry as well. A lot of folks have expressed interest in that space. There is, how do people seamlessly go from one to the other in terms of data science to machine learning. A lot of the stuff that's there is also work in progress that I will be talking about. Yeah, so just a little bit about myself. Prior to joining Uber, I was at, fortunate to be at different places. Amazon Web Services. I was like building stuff for EC2, which is kind of the bread and butter of AWS. I was at VMware before that for a long stint for about 8 years, and then at a startups before that, and I've done startups also, as part of some of these other large companies. So currently, I lead the big data query and compute infrastructure, which comprises of those are kind of the technologies areas that I dabble with at Uber. So Uber's mission is to bring reliable transportation for everyone, everywhere. That's kind of a very lofty goal, right? Transportation itself is like a multi-trillion-dollar market. Today we are kind of scratching the surface of that at Uber. And the interesting thing here with respect to transportation and data is that a lot of the big data technologies that have been built over the years by the likes of, say, Yahoo or Google or Facebook, Twitter, LinkedIn, any of those guys, it's all for web content and kind of monetizing that web content through advertisements and many other things, right? I think one thing that is unique about kind of data at Uber and some of the challenges that we face is the area to which we apply it is very unique, right? It's transportation, and nobody has really looked at the implications of big data and transportation and what are the things that are unique challenges there. So we see that a lot. We'll talk about some of them as well today. Data, we are a very highly data-driven company. Like data informs every decision at the company, and also the data separates Uber from many of our more traditional competitors. Like if you think of Uber as Uber is a transportation platform, but if you think of Uber as a ride-hailing company, it's a very intelligent or a smart ride-hailing company because that's what data differentiates and makes some of how we provide that service to our customers in a very smart way. As well as if you think of it as a food delivery company, again, data significantly differentiates how we do that much better than how a traditional food delivery company would do it. So, in terms of us moving things, data informs every decision at the company, making us very efficient. So our massive data holds deep insights, and the data team's goal is to surface those insights. The data team serves like 6,000 or so data scientists, engineers, operations managers. These are different types of, very different, diverse types of customer profiles inside the company that we serve, and the software and the systems we build cater to all of these guys. So yeah, data is what differentiates Uber. We talked about it, and so what about data is actually unique at Uber? We talk about a few different cases. In terms of the business, our mobility our platform, which means our apps, are highly pluggable. People can extend our app to build experiences for other customers, which makes even all the way from acquiring analytics really unique for Uber. Our marketplace, which is largely, if you think of the ride-hailing business, it's, if you think of the riders, drivers, and Uber, that a successful ride happens when all three parties win, right? When the rider gets a great price, the driver actually makes a good living, and then Uber makes a profit. So our marketplace has very delicate network effects, as in like when the supply of the marketplace goes down, the demand actually goes down. So and then when the demand is pretty high, and then as a result of which the eyeball time or the time for getting a ride is high, that actually and the supply is not there to match it. It affects all of the KPIs in terms of profitability, the user's experience of using the platform, so many things. So it's a very delicate marketplace. In terms of bits to atoms, we are a digital product, but we are also very, very much a physical product, right? We actually, when you open an app and you hit a button, a ride shows up. That's a magical experience. So, in terms of, there is that seamless transition between your digital footprint and then what happens in real life. And Uber also likes to do this, like spin up new lines of business. For instance, 2 years ago, roughly, we started Uber Eats, and that's significantly grown. We have started Uber Freight maybe a year ago, and that is doing very well. Recently we have talked about businesses like Uber Elevate, which is the air taxi service. So we kind of spin up new lines of business, which then has this effect, a product factor on the data, because significantly there is a new business that is now leveraging data and doing a lot of data-driven decisions, which is unique to Uber. In terms of analytics, a lot of our stuff is real time. The decisions that actually get to or that get made happen in all sorts of timelines. It happens in minutes, in terms of a few minutes. Happens in hours. Happens in days out. So there is a lot of real time implications to it. A lot of our data is spatio-temporal, which is probably not true for many data sources. But if you think about a business like Uber Eats, probably that business cares about analytics a lot in terms of what happens between 12 p.m. and say 3 p.m. and what happens between like say 7 p.m. and 9 p.m. right, which is the busiest hours for that. So we do tend to see we can do a lot of optimizations that work for the temporal aspect of it. And then almost all of what we do is very spatial in nature. Today it's two-dimensional spatial in nature, and in the future when we have things like air taxi, it will be three-dimensional spatial in nature. So ML is Uber's brain. We'll talk about ML later. We just have, the scale of Uber is also pretty high. We may not cover too much on the scale today because it's just due to time. But we'll talk about like the millions of rides that we do and stuff like that, and the implications of that for data a little bit. Consumers are growing. For us, consumers are like internal consumers of data. That's the data scientists, data engineers. As Uber continues to hire and grow, we also have to cater to that new population of people coming in. We have different kinds of workloads, both app-generated, machine-generated, as well as human-generated queries. The skill sets of the users that actually use this is very varied. The data operations folks could be typically SQL users. They may not be able to write code. And then we have we actually have some Nobel laureates in the company who are data scientists who are very good at. They're like statisticians and mathematicians, right? They cannot write code either, but they are very good at like mathematical modeling and stuff. So there is that type of user base, and then there is the typical software engineer user base, people that actually write deep neural networks and use all kinds of machine learning models and software packages. So there is that as well. So we kind of cater to a varied set of users, which means the kind of experience we have to deliver for each of them, the kind of software frameworks, the platforms we build for making them productive is very different. And we have both internal and external customers. And external customers could be like partners of Uber. It could be folks that we work with on the marketing side. And the end customers are also impacted by what the decisions we do. So the mission of the team is to move the data with global data, move the world with global data, local insights, and intelligent decisions we make. So this kind of talks about how data moves at a very high level at Uber. The data is produced by user applications or services. This could be your mobile applications. Every time you open the mobile app and look at the ETA time and close it, that's data. That could drive some insights, because that may tell that this user has a threshold for ETA, or when you open the app and look at the price of the ride to your destination and you close the app, that is an insight saying that you are price sensitive potentially. So every single thing that actually comes from the devices, the mobile devices, actually flows into the system. Similarly, if you're a rider or a driver and you're kind of taking a ride, your device emits things like has accelerometers and other sensors which emit data, which is really good information about how well the driver is driving, or is he a good or a safe driver or not. So all that data comes from the apps. So we basically ingest all data, store all data, make all data modeled and available for query. Goes through a service storage layer, which is typically your NoSQL or SQL-based storage backends. That's where the backend services serve the data out of, or they are using that data potentially for real-time, serving the business needs of making a ride happen or whatever it is that they do. Goes through then an ingestion platform, which then incrementally takes the data from these storage backends and ingests that into our Hadoop-based data lake. And then the data is stored, ETL'd, processed, modeled, made available for query there. And it also is made available. We also have a data warehouse solution that's Vertica-based, where it's also made available for. And then we drive insights, reporting, visualizations, all that stuff from that data. We'll quickly go through some data challenges, and I'll kind of pause for questions after this if you guys, we can also make this somewhat interactive. Okay, so growth and scale is a pretty big challenge. Our top line actually, our data actually grows with the number of rides we make. Which means that as we are still continuing to grow at whatever 60 or 70% year over year, that's significantly more data that we keep adding. And we also talked about the product factor, where when there is a new product, we have again a burst of data growth. Scale with employees, scale with the number of products. Talked about it. In terms of our data footprint, it's thousands of servers, hundreds of petabytes across multiple data centers, and thousands of weekly active users that we serve. We talked about the diverse user profiles. The Uber operations are really folks that are running the business day to day in any city. So these guys, typically when we launch a city, we hire a bunch of people that are ops, and then they go to that city, and they may be doing different things for that city. They may be either trying to grow the business in that city. They may be trying to grow the rider base or the driver base, depending on what it's trying to do. They may be trying to get profitable. They really have to use data very extensively to optimize whatever decisions they make locally for that city to drive those outcomes. Data scientists, we talked about them, and then the engineers are kind of probably the skill set that you're most familiar with. Typically, they're programming in Java, Go, Python. In the data world, maybe in the machine learning world, Python or R and stuff like that. So that we cater to them as well. Data quality and data freshness is a pretty big challenge. One aspect of it is also there is this continuum between what is batch and what is real time, and that gaps keeps shrinking for us all the time. We've done a lot in terms of how we incrementally ingest data, and we make all data available for query in our petabyte scale data lake within an hour. So there are many things that I think in general in industry are considered real time, where we actually run in the batch mode across our entire data set. And then we also have specialized systems that are based off of like real-time streaming analytics, either Samza or Flink-based systems, which cater for a much smaller data set, but it is much more real-time. And the real-time there is maybe minutes to hours, or minutes to less than an hour. Data quality is a big deal because there is bad data that gets into the system all the time, which then has bad repercussions on the insights and the reports that we generate. So that's a problem. And also data correctness in that context means that if there is incorrect data in one table, then there is the cascading effect on many aggregates or downstream tables that also may get affected, or downstream data sets. So it's a pretty big problem to kind of go all the way back and correct it all. Disaster multi-DC. We are already in multiple data centers just because of a single data center cannot hold all of the I think a data center has about 150 megawatts of capacity, power capacity, and our server footprint is much bigger than that. So we have to be in multi DCs for just scaling our business, and then there is also the aspect of disaster and how we recover. And as we go into 2018 and 2019, we have a rapidly evolving cloud strategy on how we want to leverage public cloud infrastructure in addition to our own data centers. Efficiency is a pretty big deal for us because, as I talked about, our data growth is slightly exponential compared to our business growth. Our business growth itself is actually somewhat exponential, has been, right? So for us, it's very important for us to keep a check on how much money we are spending on doing all the things that we do with data, in just prepping the data, making it available. So it's a very important factor. We work on that a lot. And then another challenge is security. Needless to say, with GDPR just behind us and things like SOX compliance and other things that are following us in 2019 as we think about IPO, it's a pretty big aspect of how we think about data. With that, any questions? We can fairly make it interactive. I think we are doing pretty reasonable on time. Yeah. So there are so for instance there is some partitioning on the user base as well. For instance, a subset of our data actually gets ingested into the data warehouse, which is Vertica based, and typically that is used by the data operations for a lot of interactive querying against that data set. That may be one aspect of how we think about partitioning. But in terms of our batch data set, all the users actually get to typically end up using that. So yeah, but I can think of the data operations folks typically may end up using the data warehouse, which may be a subset of the data that we have in the entire data lake. I don't think it's all of the data. It is a city ops actually. Sorry, it's maybe the data wing of the city ops, but it's a city ops part of that. So we do different things for different cities there, and we have a hybrid strategy. We, in some cases, we work with partners or we buy maps. In lot of cases, we build our own maps as well. Especially in the Bangalore office here, there is a pretty big maps team which works on a lot of the internal tooling for maps, and we also have a large maps operations team which processes a lot of the data that comes from our own mapping systems that acquire this data, processes it, labels the mapping data, and really creates maps for across the globe. So our longer term vision is that we will completely own the maps stack that Uber requires, because it's a very critical part of our software stack. In some cases, yes. In some data sets are our own, but we do augment today by buying maps as well. Great question. Hold that thought for a second. We'll talk about, when you talk about the stack, I'll answer that. I'll take one last question. That's a good question. I actually honestly do not know that answer. And I don't even know if we ever, at some point we must have been in some sort of a cloud provider. But I think for a very long time now, we have been doing our own data centers. And long time is for any, since the time when Uber kind of became a meaningfully large company, I think we've been doing our own data centers. At least this goes back 4+ years that we have been doing our own data center. Okay. Yeah, so that's a good question. Today, all of our, this is easier to answer because today the primary data centers today is all in the United States for our data workloads, right? So we have an online fleet of servers, and we have what we call the we have this hub, and internally it's called the hub and spoke model, but then our hubs are actually in the US. So our entire core data set is replicated across multiple data centers, and they're all in the US. So we'll just briefly look at the software stack. Like I said, our data lake is based off of HDFS, and we do a lot of innovation, both in terms of HDFS committers, open source committers that work in those systems, as well as we innovate surrounding HDFS by adding layers on top and stuff like that. On top of that, we have the compute resource management layers like Yarn, which comes with Hadoop, as well as we have a system called Peloton, which is a resource manager that is built on top of Mesos, which supplements Yarn. And we'll talk about why we want to do that a little later. And on top of that, we have SQL query engines and compute engines. Spark being the compute engine, we have Hive, which is a batch SQL engine, and then Presto, which is an interactive SQL engine that we use at Uber for different use cases. And Hive is primarily used for like ETLs and data prep for machine learning jobs. Runs pretty much 80% of our workload. The Hive team is also based out of the Bangalore office here. Spark is the generic compute engine we use. It's used for many complex analytics, machine learning training. Like whenever somebody wants to write code, Scala or Java or PySpark, they kind of write it to Spark. And then Presto is used for interactive querying, where it's a much smaller data set. Clusters are smaller, but you get it completely runs out of memory, and you get much better kind of latencies for your queries out of Presto. Those are the three primary query engines that we use today. And you also have this nice overlap between Hive and Spark. That is because we have a project that largely was driven out of Uber, which is called Hive on Spark. So what we have done there is we have extended Hive by taking a Hive query plan and then converting that to an execution plan on top of Spark, and then executing it on Spark. As if you guys know, Hive traditionally uses MapReduce or Tez, and Tez is another alternate engine. So we actually have Hive on Spark as another engine that can execute Hive queries. For a Spark, yes, we are in 2.1 or above. Yes, 2.1. We also have a query gateway layer, which actually nicely abstracts all the different query engines and allows people our customers to submit a query and then consume that as a service. So they don't have to worry about what engine they're submitting to. And there's also some rudimentary query translation capabilities built in there. So if it's submitted to one query engine, that can actually translate it to another query engine of sorts. So that is the layer above. And we kind of have solutions that are built on the sides, like security, efficiency and capacity, observability, which really gives us the ability to, like, we run roughly more than 1 million jobs a week that are Hive, Spark jobs, more than 1 million Hive queries a week. And roughly, if you look at all of the queries, we run somewhere between 5 and 6 million queries across the board using all the query engines in a week. So debugging a problem for us is like always a needle in the haystack. So we also significantly invest in observability tooling, which collects metrics, monitoring, logs, and looks at these problems and surfaces helpful information to the developers to debug these problems. And then All Active and Hive Sync, which is a data replication service that we have built, which essentially looks at the Hive meta store and replicates the data that is stored in HDFS across multiple clusters. So the data is highly available in case of a failure. And on top of this, we have several platforms that we have built, and these platforms help with different use cases. So we have a platform for experimentation where you can kind of go and do multi-arm banded experiments or A/B testing or many of these things just out of the box very easily. Define your experiments, run the experiments, look at the results, iterate on it pretty easily. There's a very easy to use platform on top of it. We've pretty much built our own version of Tableau, which is for all these BI tools, query builder, dash builder, map builder, chart builder for like various visualizations that you can get out of all these data sets. So it's very much a point and click interface, and you kind of get a very nice chart that keeps updating, and it's a platform that serves out these graphs, also scales them out. We have a machine learning platform. It's called Michelangelo. We have also blogged about it and stuff like that, so you can look that up. What it provides is very easy point and click entire workflow of machine learning. We'll spend a lot more time on Michelangelo, so I won't spend more time now. And then we have a lot of these things for self-service data processing. So be it data ingestion, schema definition, ingesting of the data, modeling the data, and then like landing the data from Hadoop back into things like Cassandra for model serving. So the entire workflow of data flow is actually a self-service platform as well. So I think to your question earlier about, or your question earlier about, how do people discover data sets and how do you know all this? Databook is our data discovery platform. So essentially people, all of these Hive data sets are available in Databook for discovery. You can query through it, you can look at owners, you can look at what those data sets do. There is we also have another system called Metron, which defines the business level metrics also in a discoverable way. So if somebody's already created some aggregates or some business metrics, you don't have to recreate it, you can just discover it and reuse it. That's how we kind of encourage reuse across Metron and Databook. That's how we do that. And lastly, we have this platform. We'll also spend some time talking about Data Science Workbench today. Data Science Workbench is a data science productivity platform that we have built, and my team sitting out of Palo Alto actually works on that platform. You can think of it as a Swiss Army knife of a platform. You can do anything with it. You can do experimentation with it. You can do like business intelligence with it, create dashboards and analytics. You can do machine learning model development, training, deployment in it. You can actually do data processing in it. People build ETLs in it. But essentially, what it is it's notebooks, Jupyter and RStudio notebooks, along with a whole bunch of dashboarding tools and a lot of ETLing kind of libraries and data processing libraries packaged into a platform for data scientists. So when any of these pre-existing platforms does not meet the needs, they can use DSW to do what they want to do. Any questions on the stack itself? Okay. Yeah, let me answer both questions very shortly, and we can also spend more time at the end. Our goal with Yarn is, Peloton is loosely based out of Google's Borg idea, which is a single unified resource manager across all of Google's data centers. So what it gives the efficiency of running a single resource manager. So all compute is available for all types of workloads. The problem with having a Yarn cluster separate from a Mesos cluster is that you're now kind of sharding your compute capacity, and your batch workloads cannot run on the Mesos cluster, and your online workloads cannot run on the Yarn cluster, and you may have different, so it's less efficient use of hardware. So running a same resource manager means that we have all of the hardware available for us for all types of workloads. Yeah, the idea is for us to largely, over a period of time, eliminate Yarn. So we have Peloton and Mesos be the only resource manager. Today, it's not there because of that process is still, like the development and migration is still in progress, as well as Peloton does not support MapReduce, and we still run some MapReduce jobs. So for that reason, Yarn is still there, but eventually the goal is to eliminate Yarn. And then your second question about why Presto and Spark SQL, yeah, they are somewhat redundant, but I think I also see the community going in different directions. Presto is a lot more, I think, for interactive SQL, but I think Spark is also going more on the ETL direction. So I don't know exactly how this will pan out, but I think a lot of interactive analytics usually runs a lot better with lower latencies on Presto than it does on Spark SQL. You mean the mobile device? We are making decisions for the user. I mean, we're making various types of decisions. So we may be making decisions on pricing, we may be making decisions on an ETA, we may be telling how long will it take for your food to arrive. So those are decisions we're making, but I guess that's how it reaches the user. But the analytics themselves don't, the insights do. Yes, so we also actively open source a lot of the technology we talked about here. Hive on Spark, on Presto, we have done like things like nested column pruning, and HDFS, we are doing a whole bunch of things like with observer name nodes and router-based federation to scale out our HDFS clusters to the petabyte, hundreds of petabyte scale. Lots of geospatial optimizations, Parquet optimizations for things like nested columns that we actually store, and we have extended the Parquet format for things like incremental ingestion. And Peloton is also an actively ongoing project which we intend to open source. But our model has always been where we significantly work on open source, but also internal systems that actually eventually get open source, and there are several examples of that. So we'll kind of switch to the second part of the talk today and talk about machine learning at Uber. So yeah, what's all the hype about machine learning? It's the ability of a machine to learn without being explicitly programmed. For those of you that probably are fairly new to the space, actually, as of maybe a year and a half ago, I was fairly new to the space. Identifying hidden patterns in the world based on current and historical data and use that to predict the future. It's an ability of a machine to get better at the task over a period of time, given more data and more experience of doing what it's doing. And it's also learning from mistakes, just like humans do, and improves when it's given newer or more information, right? So from that definition, for us if we are the largest transportation platform in the world, we have the most data. We generally tend to be more efficient than anybody else, or we will be more smarter as long as we're using the data very well. So typical ML workflow, you kind of define what the problem is, you create a prototype for it, you productionize the prototype that you developed, you measure, and then you iterate. Actually, this applies for any problem, not just machine learning. So what do? We actually, in the definition phase, we work with customers or cross-functional teams, understand the business needs of what problem you're trying to solve. We define objectives and KPIs early on in the process in terms of what we are trying to optimize for. We are very data-driven in what we do. Do a lot of research in terms of user research, market research. We have a market research team that actually is a central team that embeds with various businesses and helps with that process. And then, when it comes to execution, we just ruthlessly prioritize, and we define what is a minimally viable product, and then we kind of iteratively launch that, right? So the next step is we kind of build a prototype. A lot of the machine learning prototyping happens in like this cycle as well, where we get the data. Typically, things like SQL or Spark is used to use data for data prep. So it's to acquire the data, and then we do data prep, which could mean that you're cleansing the data, pre-processing it. People are probably writing Python or R, based code for things like this, typically within a notebook kind of a model, and then you're training the model typically in a CPU or a GPU, depending on what kind of model, and then you're evaluating that for computational costs and all sorts of stuff. And that's the prototyping phase. And then at the next stage, you productionize it. This is a combination typically today of data scientists and data engineers that get together for this. And we'll talk about why and some problems with that and what can we do to make that better. these guys are typically writing or translating stuff from Python or R into Java or Go, writing unit tests for them, and then kind of validating at that level. And then they deploy those models, and we have built some systems. We talked about Michelangelo. We'll talk, dive deep into that more, and we use that for deploying those models and roll out along with monitoring, and then kind of retraining strategy for that life cycle of that model. And then we make predictions, right? That's what we were doing all of this for. We do either real-time or batch predictions. And finally, we measure, as in we monitor those predictions, and we look at over a period of time if those predictions are actually degrading relative to the outcomes that they should be driving. So there is a feedback loop there. And then we gather and analyze the insights that come from it. This could be like, this kind of feedback would go into the deep dive analysis that product folks would do into road mapping for the product and what we should be doing next and things like that. And kind of that's a cycle. So you kind of use that data to go back and understand business needs and go back to do this. So it's a full cycle. For doing the entire cycle easily, or at least a large portion of the cycle easily, we have a platform, machine learning platform called Michelangelo that was developed internally at Uber, and it's used extensively. So what is the mission? It's to enable engineers and data scientists across the company to easily build and deploy machine learning solutions at scale. And we'll talk more about some of the use cases, but it is pretty used extensively at Uber. So what kind of stuff does it do? It's machine learning as a service, delivered as a service. Provides scalable infrastructure for training and serving models. Provides the workflows required for and the tools required for prototyping, the iteration, and to productionize eventually. Has feature sharing, reuse of models that you have built, as well as discovery of these through the feature store, and has deep integration with Uber's infrastructure tooling, be it in the compute space or the networking space, to kind of acquire data, or the data space, data infrastructure space, to acquire data, publish, and do predictions. So, I mean, when I moved from Amazon, I was kind of first kind of baffled by the scale at which Uber applies machine learning. Just rule-based systems just are dwarfed by the number of machine learning systems that actually get deployed. Primarily, I think because of the ease of their development, because some of these systems and the platforms we've built makes it really easy to develop models, take some data, throw that data against a bunch of models, look at how 3 or 4 models perform, pick one and productionize, rather than just writing code for it. And it makes it really easy. Therefore, it's applied to a whole bunch of use cases. Just a few use cases here, like rider-driver matching. There is lots of applications of machine learning there. Route planning, what's the best route to take? Taking into account things like traffic and other considerations for that route planning. Uber pool optimization is like a phenomenal piece of engineering where you have all these different routes that could be taken, and you have all these riders and drivers that you're trying to, or multiple riders you're trying to match up to a driver, and what is the optimal route that actually minimizes the ETA for all of them as a group, but then also minimizes the price as well, right? So it's a very interesting optimization problem. ETA and estimated time of delivery for like ETA for your cars to arrive, ETD for like Uber Eats or something like that. Trip pricing is again extensive use of machine learning where it's very important for us to give the right price to the rider, so they actually take the ride instead of maybe choosing an alternate mode of transportation. But it's also equally important for us to make sure that price works for the driver, and it also works for Uber, because at the end of the day, Uber has to make a profit out of this transaction. Otherwise, that's not a healthy marketplace. So it's and then if any mistake that we do in that pricing means that either the rider is unhappy or they don't take the ride, or Uber makes a loss, or the driver is unhappy. So the outcomes actually have to be good for all 3 parties. Demand shaping, projection, things like we may just have a lot of supply in an area, but then we may not have enough demand, or we may have a lot of demand in the area and supply is not there. So we could do things like, why doesn't the rider walk like a block, or why don't we all go to a pool to a place where it's easy to pick up, or we increase the price so it actually is inconvenient for somebody to take a ride. So many of these things actually we do to shape the demand based on the supply. Image and object recognition for maps has just, or the automated autonomous vehicles has heavy use of machine learning. Fraud detection, because I think back when, even today, but then I think at this point, I mean, the thing with fraud is that the fraudsters usually keep pace with us all the time. So there are new types of frauds that they keep developing, and our risk safety and fraud detection teams kind of keep looking at all types of frauds and detecting it. And you probably are familiar with so many kinds of frauds that I think that some drivers may have been doing in the past. Safe driver dispatch, incentive allocation, just the list goes on. So many machine learning based systems that we deploy. Yeah, today, so it roughly powers the movement of like 16 million people and things daily. That's a lot of machine learning that actually happens at Uber. And it's only the beginning, because I think Uber as a company is fairly young, right? If you think of so many other companies that are probably have been out there for like decades or so, Uber is still a fairly young company. So this is just the beginning for Uber. So we'll look at some use cases briefly and then dive into some of the machine learning platforms. So I won't go through the slide, but like time modeling is a very interesting use case where we have to model time for the whole entire Uber Eats delivery. We have to tell the eater how long will the food arrive in, and then they make a choice, and then we need to tell the restaurant what prep time they have, and then we have to tell the delivery partner when to go to the restaurant to pick it up, right? So kind of the time modeling has to work completely end to end. So very interesting use case for machine learning. And just generally rides the ETA calculation, how long is it going to take for someone to come here, is a lot of factors in terms of traffic that's going on, and we look at how historically that's happened. Estimated time of delivery, we have done some interesting stuff to reduce that by 26%, and also just simple search results and all that stuff has a lot of implications in the Uber Eats space. Again, some of these more typical uses of machine learning that you probably see in other kind of search companies, like maybe ranking of stores or ranking of menu within a store, also have typical clustering and other use cases for machine learning. Also, a lot of use case in kind of customer grievance resolution. We actually have a team in the Bangalore office called Customer Obsession, which is starting up, which is going to exclusively look into this problem space of all the different customer grievances or tickets that come into the system, and how we apply various technologies, including machine learning, to either address those grievances in real time or over a period of time reduce the funnel. So the human being having to look at that ticket and then resolve that problem is very small. So we look at data science at Uber, how we do that. So roughly maybe early 2016, this is when before I joined, and this was kind of the snapshot of what Uber's data science was like. We were still having a good 3x growth in data science community year over year. People were using Python and R-based machine learning for a lot of their stuff, but it was all do it yourself on your laptops. So there was no reliability or software support, platform support for it. Moving a Python model to production was very, very hard. There was a proliferation of tools and libraries and systems across the board that was being used, so there is no consistency. If a data scientist moved from one organization to another, they had to completely relearn the tooling. And the things that did not scale for thousands of users or data scientists, and there was no collaboration. People could not really take their model and say how does it look, how can you improve it, or how can I share it with others? Because the other problem is we were also growing at a pace where maybe the solutions that actually applied for one country or one city applies for another. So you just have that cross learning had to happen, and then security compliance were just non-existent, which just wouldn't fly. So what my team did, we kicked off a very small team to do this platform called Data Science Workbench, essentially a data science productivity platform that solved these problems. So the problem was that we have, the productivity of data scientists was significantly suffering due to these fragmented set of tools and an unreliable infrastructure. DSW basically packed a variety of these tools, essentially notebook interfaces such as RStudio, Python, or data processing libraries, NumPy, scikit-learn, a whole bunch of other libraries that they typically used, as well as dashboarding tools like Python dashboards, Bokeh, and so many other things into a single scalable platform and delivered that as a service. And all the popular data science tools were available for them in a single umbrella. It scaled for thousands of users. It was powered by Hadoop in terms of being able to do PySpark and other things at scale right from their notebook, as well as these were cloud-managed desktops. They started using them as cloud-managed desktops, where all their work was 100% backed up all the time. So it was very there's no loss of productivity, and they could actually collaborate easily. And we'll talk about some collaboration stuff that we've built. Used by data scientists, engineers, and analysts, so all kinds of users today to do various things, relative to model building, machine learning, just analytics, ETLs. They do all sorts of stuff there, and then data is at the core of the product, so it's actually a pretty important platform for Uber. So the goal is to unleash the productivity of data science community at Uber by providing a scalable infrastructure and tooling and customization and support. So what we have now, fully hosted environment. It's a one-click deploy for getting your notebooks up and running. It's a completely pre-baked environment. You can actually customize the sessions. Once you launch them, you can actually add more packages or whatever that you need to customize whatever libraries that you want. It's wired to all the internal sources and compute engines and monitoring and stuff like that. It's multi-DZ, it's secure. People can share, publish their notebooks, get comments, get feedback on that, and they can also create shiny dashboards, which is very extensively used at Uber. We'll do a quick walkthrough. I won't spend too much time because I want at least maybe 10 more minutes to spend on the other stuff. Yeah, so this is kind of the UI, what the UI looks like. You kind of have a list of sessions. You can create either RStudio or Jupyter sessions today. It's very pluggable to add additional notebook interfaces such as Zeppelin or whatever. We're also actively thinking of open sourcing this whole work. This is how the sessions look. You can kind of look at all your files. There is an ability to kind of upload files and manage files directly through it, which is backed by a NFS filer or a Ceph filer for persistent storage of data. You can also choose various types of backends that you want to, or kernels that you want to execute against. Various Python kernels or PySpark kernels if you want to execute it against a backend. And Scala Spark Magic essentially allows you to write Scala code in a notebook and interactively execute it. So you can do pretty much the same thing you do for Python, where you run a set of one line of code, executes on the cluster, comes back and gives you the results, and you can visualize it right there. So it pretty much gives you interactive debuggability for Scala code you write in a notebook interface. So kind of this is how customers still get the native Jupyter or RStudio experience from a UI perspective, and this is kind of the file explorer, how you can kind of look at various lines of code and also just do it from the explorer. People can also very quickly take a notebook that they develop and then schedule a job out of it, and then this would keep running. So you don't have to. This is a very lightweight DAG of sorts where you can periodically execute a notebook and maybe drive a dashboard or do an ETL or something like that right from your notebook. There's also very rich visualizations available in terms of Shiny and Python dashboards, which can be created right from the single platform that you have, the DSW. You can create these dashboards, share it with your colleagues under authorization and auth and auth-z, and make sure that it's securely shared, and it also scales out. So if there are more folks that come and visit that particular visualization or that dashboard, the infrastructure scales out, so the service doesn't go down. So let's talk about some data science challenges today that we face at Uber. So one is the environment challenge, which is there's always a gap between experimentation and production. This could be in terms of I did all this in the notebook, and then I now have to productionize it, and then I get different functionality or I get different performance or results just because my environment is different, right? And then therefore the reproducibility of a model is a big problem, as well as repeatability of experiments. Even if you're doing experimentation, not production, because the environments change, because maybe you pulled new software packages and you don't have good versioning, you just may not get good, or the infrastructure changed and maybe it become much faster, or like compute infrastructure changed or something like that. Your experiments are not repeatable. And then there's also a durability problem, because somebody may have customized a lot of their sessions by installing software packages inside that notebook, but then the machine crashes and all of their work is lost. So something that we are actively working on, and which is probably very generically useful for the community that we could open source, is this thing called DSW environments, where essentially we can preserve a snapshot of everything that you have in your data science experimentation environment. The base image from which the container came from, custom packages that you might have installed, so list of all those and being able to recreate that, configuration and OS environments that you might have tweaked, all the code that you wrote in the notebooks version through Git, and then like snapshot of the file system. Like if you're directly creating files, that also is part of the configuration. We take a snapshot of that from the filer backend and then be able to reproduce that. And what this also can do is, for the production use case, you may not need all of the packages, so we can also just do a highly performant Docker image that can be exported from this session, which then can be directly productionized. So we'll talk about this thing that I call the chicken and egg problem of data science. So data science experimentation is expensive, right? So to justify investments in complexity, there is a need to evaluate or gauge the impact of whatever you're trying to do. And so, but how do you kind of measure impact without prototyping and or validating if what your results are correct? Or how do you assess the correctness of whatever reference implementation which you're actually implementing, right? So the first step being something like somebody does in Python or R. If you have to implement it using Java, you directly take a hit of multiple weeks where you need to handhold somebody who does not know data science, an engineer typically, who needs to write these algorithms and productionize and deploy them. So the current state of ML tooling in the industry just does not cut it. What we have seen is that it actually discourages exploration and experimentation, because of people start doubting whether it's actually needed. There is a huge expense of multiple weeks to take this model and productionize it. Is it actually valuable at all, right? And then, so some of the existing platforms that we have are not cutting it for us, as well as what this means is that sometimes the engineering teams completely skip the initial part, and then they go into production implementations, and they hope for the best. And what happens is that in production, these systems don't deliver the outcome they want, and then they have to roll back and rethink this. So this is a huge problem. So in terms of what this causes between a data scientist and a data engineer, is this whole empathy gap, right? I think these two guys don't understand each other. They're both really good at what they do. The data scientist is really good at math and statistics and modeling, and the data engineer is really good at writing very scalable code, deploying them in production, managing them very well, monitoring it, and they just don't talk to each other very well in many cases. So the empathy gap is like the data scientist thinks that engineers see only the implementation costs, or if they could see the potential of my innovative ideas, maybe they will actually help me better. And the data scientists or data engineers think that the data scientists don't get the challenges of writing scalable software and managing this infrastructure. Or how many of you have seen what I'm talking about? What am I talking about? Okay, yeah, that too. But have you seen Silicon Valley? There are these two guys who actually are kind of in this. One is an infra guy and another is an algorithm guy. Very loosely, they keep talking about how the infra guy doesn't understand the algorithm guy, and the algorithm guy doesn't understand the infra guy. Which is very similar between like a data scientist and kind of our conversations that go. So like moving bits at scale isn't easy. So they're both right. So kind of what we are doing to bridge the empathy gap is we're taking these two systems that we have built internally. One is Data Science Workbench, and the other is Michelangelo, and Michelangelo deals a lot with the production aspects of machine learning, and Data Science Workbench is this productivity platform, and kind of bringing them closer to each other, so there is a more seamless workflow that's possible for the entire ML workflow that we saw earlier. So what does the golden data science ML workflow look like? Ideally, it's a streamlined workflow from a single platform where somebody can do data prep, feature transformation. They can model and iterate on that model. They can do online experimentation or do large-scale backtesting with lots of data. And then they can productionize it right from there by writing a simple line of code, or they can push a button and they can repeat that whole thing. And once they are done, they're able to take all of that and share that knowledge with everybody in the organization with the right controls, so people don't have to do it again. So all these experiments are recorded, their knowledge is recorded, and if something applied for a particular city in a point in time, another ops person can go and discover that experiment and look at whether that applies to me. Can I deploy that model? Would I get a good result or not? Is something that is possible without doing the experimentation. So in terms of data prep, what does it look like? We today, so some of this is work in progress. We are like multiple teams working with each other to kind of realize this vision. So launch a data science workbench environment on a chosen instance type. Kind of ask you a small instance, large instance, CPU or GPU, and we are kind of working on the whole cloud enablement. It's typically things like TensorFlow tends to run much better on TPUs on the Google Cloud platform. So that is something that's in the future that we're working on. So you kind of get this data science workbench instance environment which you have pre-packaged. You can interactively prepare a data set using SQL or PySpark commands right from DSW, and PySpark in this case meaning that it's going to run on the entire Hadoop cluster, so you can actually prep the data or ETL it or create the feature vectors at scale, right? It's completely data parallel, and persist that into the data lake. Quickly collect large samples of data into memory for modeling. If you're doing things which is completely in memory, you can also like request for large instances that you can load maybe terabytes of data into memory and then crunch them. And you can do model iteration, which is like developing these models or developing the training code for these models also by writing code in DSW. And all of this source code automatically gets git committed. So if something crashes, you actually have that to go back and resume your work right from the environment. You can test all these different models in the notebook, visualize them by creating dashboards in Python or Shiny dashboards right from DSW. And then you can collaborate with your teammates by either sharing these notebooks or dashboards and getting feedback. And one of the advanced things that we're working on is also just collaborative editing. So you can have more than we are a fairly global organization with data scientists that work from various different parts of the world. So where more than one person can log into the platform and kind of interactively edit the notebook by passing control back and forth on this one notebook that probably they're using. Experimentation and backtesting being that you can then take this model that you developed right in DSW, snapshot the model artifacts, be it the parameters, the code, the dependencies, all into this DSW environment, and then take that environment and register that with Michelangelo, which is the production platform we talked about, its model store. So export the production image, which we talked about earlier, highly optimized for production, into Michelangelo, and then from there you can evaluate your models against large amounts of data, be it like batch coding and things, launch PySpark jobs, or run your models live against traffic by productionizing it. Our cluster is typically like a online service that is used for productionizing, and then Cassandra, that's a backing store from which the model gets served out. So all of that can happen right from the same platform without having to leave it. So what this means is at the end of this, you actually can write something in PySpark and then click a button and go through the whole productionizing of this model, and without having to engage a data engineer for a data scientist, right? So once you do this, you can then decide whether based on your backtesting and experimental results, do you want to engage an engineering team and then choose to productionize this using maybe native platforms like Caffe 2 or TensorFlow or which may be much more optimized, so you can do that. Or you can just look at to see if this model is performant enough, just leave it running. You don't have to necessarily convert that into another implementation for production. And the other very important thing that it also gives you is you can take a model and over a period of time, let's say a few months later, it's not working well, you can take that model and then completely recreate the entire environment that was used to build that model. So the whole DSW environment I talked about, which has what was the base image, what was all the packages that we installed, what versions of them, what was the configuration, because those are all saved in the network file and snapshot.